So today we're going to be working on PV work in chemistry. So the question is, a piston has an external pressure of 11 bar. How much work has been done in joules if the cylinder goes from a volume of 0.180 liters to 0.65 liters? So in this question, we're actually going to be highlighting what they're actually asking for. So a piston usually means it's going to be a work problem, obviously, and that we have a working pressure of 11 bar. So that's our pressure. So when we talk about work, we're going to be looking for the equation work equals negative pressure delta V. And we're just going to make sure that we actually have the information for this equation. So we need work done in joules. Okay, so that's going to be specified for our end answer. And so cylinder also can help us later, but we also have this volume change available. So then we both have the P and the delta V available to us. So what we can do is actually state the variables in the equation. So P, our pressure, will equal 11.0 bars, which is awesome. That's exactly what we need. And now delta V will be our final volume minus our initial volume. So looking at the equation, it went from 0.180 liters to 0.650 liters. So how we can actually draw this out in order to explain it is that our pressure, which didn't change, made it so that this container, like this gas, was actually filling only 0.180 liters of this gas. But then after the actual work has been done by the system, the amount of volume actually increases. So we still have the same amount of pressure actually being exerted on the gas, but we're actually having the increase to be 0.65 liters, which means that there is a total difference here by doing work. So that change is actually what we're seeing here by doing our final minus our initial, just because it increased. So if we actually plug in our values, we'll have 0.650 liters minus our 0.180 liters. And if you calculate that, which I'm not going to do here, I'm actually going to write down the answer of 0.470 liters. So that's our change that's going to be put into this part of the equation. And since we already have pressure, which we've already stated here, we're actually going to be able to just plug it in. So also, this negative sign does stay. It is important, so we have to make sure it's there. But when we're actually stating these things, making sure that we're carrying the right negative or the right positive is really, really important. So our pressure was, again, 11.0 bar. And then our change in volume was this value. So then when we do it all and we put everything in, we get to negative 5.17 liters per bar, which is an accurate measurement. It is actually a proper unit for work. Unfortunately, we actually have to convert. And the only reason why we're doing that is because they actually stated in joules that they wanted the answer in. So how do we do that? Well, I'm just going to restate what we already have above, just so then you can actually see what's happening. So we have liters per bar, sorry, not per bar, liter bars. And then our conversion rate is 100 joules per 1 liter bar. So therefore, because our liter bar and our liter bar will cancel out due to dimensional analysis, we'll only be left with our joules. So then what we'll have is negative 517 joules as our work. you can obviously state that as like, therefore, the work done was negative 517 joules, and this makes sense because the actual system itself is doing work and using energy in order to push this up again, to push against the actual pressure that's constant. So again, everything kind of works out in terms of everything equaling together. We have the right units and everything, but I just wanted to explain why I used this in order to convert. So I didn't just make it up. It actually comes from the division of two common values of the R constant. So the two values of R constant that I actually used were 8.314 joules per mole. So this is like per mole, but just inverse moles. So it's just a different way of writing it. And then per Kelvin, and then that's divided by another R constant, 0.8314 liters, bars, moles per liter, and sorry, inverse moles, and then inverse Kelvin. So then we actually exclude all of these things and we just kind of cancel them out. It actually works out to be exactly what we have above, which is 100 joules per 1 liter bar. So that's exactly what we put in here in order to get the right units that they asked for. The next one is, a system releases 699 kilojoules of heat and does 100 kilojoules of work on the surroundings. What is the change in the internal energy of the system? All right, so we just have to ask ourselves, what are they giving us in terms of our information? So reading the question more carefully will actually give us most of the answers. So a system releases is key. Because like as we've seen with the other questions, the negative sign is really important in terms of the system is losing something. All right, so releases 699 kilojoules of heat. All right, so heat is actually stated by the variable Q and does 100 kilojoules of work. All right, so then this would be variable W on the surroundings. So this means in both cases, we'd actually be doing kind of like the negatives of energy and work here. So what is the change in the internal, energy of the system? So pretty much the internal energy system can be written two ways. I've seen it been done for both. So it can either be delta E or delta U. This actually is a little bit more common in calorimetry that I've seen in first year chemistry. So I would actually suggest using this one. But when we're actually doing any sort of internal energy thing, we're just actually finding the sum of everything that's being done. So really it's actually the heat plus the work being done that is the total energy that's happening in this system. So what we actually really need to find out is the signs. The signs are what's going to actually be the most important here. So what can we do in order to state this? So Q, we know is the heat. So when we read it as saying releases 699 kilojoules of heat, that means it's actually losing energy. So it makes sense to actually write it as negative kilojoules, just because, again, it's doing work on the surroundings. It's not gaining anything. So work will also be a negative, and it'll be negative 100 kilojoules, again, because it's doing work on the surroundings. So again, in both cases, we're actually losing things. So since we've stated our variables and we've stated our equations, it'd be full communication marks, and also highlighting things for yourself will be really helpful in long answer questions. I know a lot of people that actually bring highlighters and different color pens into exams, just because it makes it easier for them to see and differentiate equations. So we're just going to plug in exactly what we see here. So Q, or the heat released, was negative 699 kilojoules. And here, even though this has a plus, in the end we're actually going to be doing a minus since we did work. All right, so again, I'm just expanding it just so that it looks a little bit neater and is a little bit easier for you to follow. And then just adding it all up will be negative 799 kilojoules of internal energy. So this is actually the change in internal energy, but this will be what you need, and there's really no need for you to convert into any other units either. So I hope this answered some common questions about calorimetry and PV work in order to get you started into more complicated questions in chemistry.